Today, I'm Chin-Wei, and my colleague, I, Victor, we're going to give a lecture on diffusion-based models. And we are from Microsoft Research for Science from this beautiful city of Amsterdam. And so typically, like when people talk about journey models or diffusion-based models, they show these beautiful images of from DALL-E or Imagen or beautiful videos. I kind of want to motivate it from a different point of view from science, since we work on AI applied to science domain, specifically in chemistry. Like our team is composed of researchers from people with a background in ML, in AI, and also with a background in chemistry, quantum chemistry, material science, etc. And there's a lot of applications in the chemistry domain. For instance, we can use journey models to generate like small drug-like molecules, the molecular graphs, so that we can use that for drug design. We can also use diffusion-based models for protein structure simulation to understand the folding behavior of proteins. And we can also use these models for generating inorganic materials and also to assist in the design of these materials. And we can also think about a different kind of axis. For instance, in the temporal domain axis, how can we use diffusion-based models or journey models to accelerate dynamic simulation for molecules? And on the length scale, we can also like generate these structures, but generate using a different kind of coarse-grained representation, so that instead of modeling the atomistic representation, we can model a more coarse-grained representation, which will help us scale up to larger structures, and that will help us to study bulk properties more efficiently, hopefully. So today, with that application in mind, today's lecture is going to be more about how to design models, like diffusion-based models, to generate structures, samples, like images, like molecules, like audio or text even. So that's going to be the first part of the section. And then the second part of the section, Victor will tell us about how to adapt diffusion-based models to model molecules, specifically with equivariant architectures. And the last section will be a workshop, and we're going to be actually using our laptop to do some coding work. And I like to give some credit to my colleagues from Microsoft who very generously lend us their slides. Yeah. OK, so with that, I'm going to talk about diffusion-based models. To talk about diffusion-based models, I want to just have a quick recap of VAEs and normalizing flows. Also, just a quick question. Today, Jess also talked about these two families, right? Like VAEs, normalizing flows. Cool. All right, so I don't have to spend too much time on it. So a VAE essentially is a latent variable model. So what is a latent variable model? A quick recap. We will have our data, which is the observed random variable. And our modeling choice here is that we have a set of random vectors that is not observed. And because of the fact that we have a linear variable model, we have an intractable likelihood, and there's a lot of approximation steps you have to go through in order to derive a optimizable objective. And there's also, like VAEs also comes with a lot of modeling choice in terms of how you can factorize your latent vectors. Yeah. Right, so I was just talking about like in the design of VAE, there's a lot of choice you can make in terms of how you're going to factorize your model, your latent vectors. A particular choice is a Markovian choice, for instance. So we can sample our latent vector, let's say T, and then we decode it kind of iteratively like this, but we only condition on previous time step. And also for our inference model, we can also condition it on the previous state instead of being fully autoregressive. That's a choice, and you can make many different kinds of choices. And this particular choice has a resemblance to normalizing flow. Because for VAE, you have this inference machine. You would also have this decoder machine, which is the reconstruction. They are kind of dual to each other. So at the same time, you want to model the likelihood of data. You also want to match these two networks. For a normalizing flow, it kind of overcomes this difficulty by saying, OK, what if we just have a fully invertible architecture? So we don't have to worry about reconstruction. And in this case, you can derive your reconstruction network by taking the inverse of an encoder, basically. And for normalizing flow, that has the benefit of, okay, I can just focus on one network and focus on transforming our data into the prior distribution. So, destroying the structure in the data and get something that's fully unstructured. And to sample, we sample from the prior and use the inverse function of the encoding network. Okay, so far so good, just a recap. All right. However, that kind of is, there's two shortcomings of a very deep VAE and normalizing flows. The first one is that, as we see in the previous slide, there are multiple layers, right? And in the loss of these models, VAEs or normalizing flows, as you go deeper, the more loss terms you're going to have in your objective. So your complexity for training becomes linear in depth. So if you have 1,000 layers, you have to have 1,000 loss terms. And that doesn't scale well. That's the first thing. The other thing is that either normalizing flow or the very deep VAE, the transformation from your data distribution to a prior distribution is very arbitrary. You can transform this cross distribution into a standard Gaussian distribution in a very arbitrary way. For VAE, if you choose this path, you have to match your decoder with your encoder. But if you choose another path, you have to adapt your decoder again. Normalizing flow kind of circumvent this dynamic problem of matching two networks, but at a cost of a very limited architecture choice, because you have to constrain your normalizing flow to be invertible, and also you have some properties like you want to be able to compute the log determinant of Jacobian, etc. So it's also not good. And diffusion-based models sort of tackles these two big problems of a very deep VAE or deep normalizing flows by saying that, okay, we don't have this linear time complexity, and also it has a fixed dynamics for transformation. All right, so what is a diffusion-based model? A diffusion-based model basically starts from defining the forward process that destroys the structure of your data by adding a little bit of noise each time, and it comes with a German model, which is learning to revert the forward dynamics. Okay, so we have this noisy process going from the left to right, and we learn a journey model that reverts the dynamics. There are different perspectives of a diffusion-based model. One is you can sort of see the noisy procedure as the encoder network of a VAE, so you're performing inference with a particular encoder network. And the forward process is the generator in the VAE. And another very important and interesting perspective is score matching, which I probably won't spend too much time on, but roughly speaking, it's saying that, let's say, oops. For score matching, we're trying to approximate this guy here. So suppose this is ZT. So ZT is our data plus some noise at time set t. So with time set being big, there's going to be a lot of noise. With time set being small, there's going to be a very small amount of noise. So going from left to right, we have a less and less structure. We're trying to approximate the score function, which is defined to be the gradient of this log probability, the gradient with respect to the spatial coordinates. And being able to do that will allow us to sample from that distribution well. For instance, you can perform long-term dynamics or all sorts of MCMC techniques. So diffusion-based models sort of marries these two branches of things. The first thing is MCMC for energy-based model. So this is basically the gradient of an energy function, and a deep latent variable models. Okay, and we're going to focus on the first perspective in this lecture. Okay, so just a quick recap of VAE on the notations. For latent variable model like VAE, we would define a joint probability over our observed variable and also a latent vector z. And the marginal likelihood of x would be basically the joint, but integrating out the latent vector z. And typically, we would assume a factorization that will allow us to sample more efficiently from the model. For instance, we sample z first, and we sample x conditioned on z. And this is called the ancestral sampling. Okay, and the goal here is to make sure the probability of P of X resembles the distribution of the data. Okay, and we would like to do that by performing maximum likelihood. Okay, and if we can approximate the data distribution well, we can sample from using this procedure to mimic the data. All right. All right, so I'm just gonna quickly derive the elbow. I'm sure you did this several times this week already, just so that we can get it going. So the typical problem with a linear variable model here is that in order to integrate out this Z, I mean, we cannot easily do that because our decoder network usually is very nonlinear and we don't have conjugate prior, etc. So this doesn't have a very convenient expression, the log integration. So we have to approximate the whole thing. First of all, we can introduce the variational distribution, Q of Z given X, Z given X, and P of X, Z, Vz. Okay, so we can do that because Q divided by Q is 1. And then we interpret the whole thing as an expectation over Q of Z given X. So this whole thing, oh, whoops. This whole thing is the expectation. Okay, and then we apply our favorite Jensen's inequality, like swapping expectation and log, because log is a concave function. Then we have the lower bound, the evidence lower bound. Okay, so this is the elbow, just to recap. And you can also look at the next slide, which is easier to read than my handwriting. And for a diffusion-based model, as I said before, we're going to introduce a bunch of latent variables. So, because our diffusion process has multiple iterations of denoising, so we're going to denote them by Z1 up to ZT. We go through the same procedure. We introduce a sequence of a distribution over a sequence of random variables that are denoted by Q of Z1 to ZT, conditional X. And Q divided by Q is 1. Interpret this as expectation. Log of expectation can be lower bounded by an expectation of log because the log is concave. So voila, we have a lower bound for a very deep latent variable model. Okay, and now the next question is, we have our choices of modeling here. We can choose to factorize our German model, P theta, and our inference machine. We can factorize them however we want. So for diffusion-based model, we're gonna factorize them in a Markovian way. So that means for the forward process that destroys the structure, we're gonna iteratively add noise to the previous state, okay? And we only add noise to the previous state, and we don't care about anything that's before me. So that's Markovian. For the backward process, we're gonna assume the same assumption. It's also Markovian, but it goes from ZT, which is sample from the prior, and then ZT minus 1 given ZT, and then iteratively we have X given Z1. Okay, so it's this Markovian procedure. All right, any questions so far? Cool. All right, and now, why do we choose this Markovian property? Basically, there's going to be some magic in the arrangement of the terms that will give us some benefits. Yeah, question? Yeah, good question. So this is sort of similar to a normalizing flow. We're going to maintain the full dimensionality of the data, but there's also diffusion-based models kind of operating in a different space than the data. For instance, you can have a diffusion model on the latent space. But yeah, today I'm going to focus on diffusion model on the full dimensionality, like pixel-wise diffusion, for instance, for images. Okay, so this is our choice of factorization. And we can then plug this in our elbow, right? So we can factorize our P according to this factorization. And we're gonna see some benefit here. So this is just by definition, right? So this is definition of P, definition of P. Okay, and for the inference part, I'm gonna do something slightly different, right? So you can of course do the same thing as your choice of factorization. You can, for instance, do that, but we're not doing that. And you know that's also part of the magic of a diffusion-based model, as opposed to a vanilla deep VAE. Instead of plugging in the factorization of our choice, we're going to factorize it using the product rule, but following the same order as our generation. So we'll go from ZT minus 1 down to Z1. We are also going to do the same thing for Q, for the inference part. We're going to go from ZT minus 1, and then down to Z1. Okay, and we can choose any ordering, and as long as we maintain all of our history, and this is simply just the product rule of the probability. Okay, you can do that for any joint distribution. You can factorize it any order in any order. Okay, and so the magic here is that since we have this Q network, okay, let's say this is ZT minus 1, ZT plus 1, and so on and so forth, and I also have X. Okay, and we want to perform inference on ZT minus 1. That's the thing we care about, ZT minus 1. We want to condition on everything in the future, and also X. Okay, for people who know about probabilistic graphical model or familiar with Markov networks like this, there's an algorithm called the baseball algorithm, which is a funny name. The idea here is that if we condition on this guy here, then we can flow the information. If we can flow back, this kind of blocks the way to the future. Then the thing that we care about, which is ZT minus 1, will be independent of everything that's on the other side of the shaded ball here. Okay, so that tells us what? That tells us for this particular graph, if we condition on the present, our past is independent of the future. So that allows us to drop everything in the future here. Okay, so that's a very convenient trick, because now we also have this, also Markov reverse process. So we sample ZT from X, everything is conditioned on X, and also the lowercase ZT minus 1 condition on ZT, and nothing in the future, because we have conditional independence. Okay? And the benefit of this factorization now then is we can organize our terms in the same order. Right? So the first term will give us the KO divergence between our prior and also our marginal Q of ZT given X. And all of these, they are all comparable with the P part. So they are all KL divergence. KL divergence is between ZT minus 1 given ZT and X, and P of ZT minus 1 given ZT. Okay, and the last term is a single reconstruction term of Z1, of X given Z1. Okay, so just simple rearrangement. So one of the benefits here is that we see there's a KL divergence, for instance. Whenever we see a KL divergence, there's the benefit of, okay, we can figure out, is there any analytical solution? If there's an analytical solution, we can, just, optimize it that way instead of doing sampling. So there's the benefit of variance reduction. And then, and then there are 3 terms in general. And so we're gonna focus on the terms in between for now. Okay. So for practical training of this model, because we have the thing in between, that's a thing that scales linearly in a number of layers. We want to be able to perform simulation-free inference, and that's sort of the trick that allows us to train this model in a constant time, compared to a deep VAE, right? Because at the beginning I said in the deep VAE, as we have more and more layers, we have more and more terms in the loss function, and that doesn't scale well. So the first requirement is that we want to be able to sample from this Q distribution so that we can estimate this loss term for a particular time step T. And the second requirement is that we want to be able to express this like reverse of the forward process, condition on X, and also the KO divergence compared to the model P of Z minus 1 given ZT. Okay? And the cool thing is that we can make very simple assumption on our modeling choices in the forward and reverse process. For instance, for like data living in the real space, like image pixels or molecules, we can use a Gaussian distribution, Gaussian family. For discrete data, for text, for instance, we can use the binomial family. Okay, and for these two choices, assuming linear diffusion, for instance, then we would have a closed form formula for both of these requirements. Okay, so all that seems very abstract for now. We're going to look at one example using Gaussian for real value data. So far, so good. Any questions? Yeah.
The previous slide, in which you mentioned how we arrive at the three terms.
Yeah.
One more previous, please. Could you please maybe in short explain again how we go from the definition of P and Q? Because in the Q, there is this thing that Q of ZT given ZT minus 1, and the later one we are coming to ZT, Q of ZT minus 1 given ZT. How is that reverse?
Yeah. So the question is, so in the choice, we choose to factorize it this way, right? We choose to factorize it as ZT given T minus 1, etc. But here we factorize in the other order. Okay, so this is a choice of the modeling of the inference. But for any joint distribution, we can factorize it as a product of distributions in any order. That's the product rule of probability. Yeah, but in this factorization, you have to keep track of all of your histories.
So how are we using that thing?
So we use this fact when we drop the dependencies here. Yeah, because we make this assumption, this is equal to this. Yeah, because it's because of the Markov condition of independence. Yeah. Okay. So this is assumption of Q, and we derive this from this. Cool. Any more questions? We have some beats. Yeah.
Just one general question about calling these latents. In the case of VAEs, there is a lot of information in latent variables, right? You're learning a low-dimensional representation, and that's not the case here. Can we still extract any information from these latents?
So, interesting. So the question is, can we extract any information from this latent variable? And I guess whether it's legit to call them latent variables, right? Like, it's a good question. So compared to VAE, in this framework, these latent variables, they still contain information of our original data in the sense that as long as you don't go to the very high noise level, you can still sort of see the contour of the data, right? So the noisy data is still related to the original data. So it's not completely independent. So of course there's information in that sense, but it's also not a very structured latent variable in the sense of, for instance, in VAE, you would typically think of your latent vectors as some meaningful representation, for instance, of your original data, right? Like, okay, if we go in that direction, it means someone's smiling or someone is frowning, for instance. And we don't have that kind of interpretability of a latent variable here, in that sense. Yeah. Questions? Yeah.
When you assume that when you mentioned this Gaussian family of for closed form, we are going at a pixel level, if I understood it.
Yeah, we are going back to oops, I don't know why. Yeah, we're going back to the pixel level.
So if we want to have this thing that for every pixel there is this Gaussian.
Exactly. So imagine you have an image, you want to model the image distribution, we simply just add noise to the pixels. Yeah. find a prediction for any conditional. You can figure out mean, the standard deviation, covariance. But maybe in the original paper from the DPN, diffusion-based model, there's probably the simpler derivation. So this is simply just a derivation of the mean, and we plug in the mean of the reverse Q here. And repriming ZT now using the mean and standard deviation of the Q we just saw from a standard Gaussian. We introduce a new variable which is standard Gaussian noise. Now we can, with some rearrangement, which I'm not showing here, this is many steps, as you can see already. Mu tail can be rewritten as a function of ZT only and epsilon. And ZT depends on X implicitly because the mean depends on X. It's a weighted average between X and epsilon. And we see now the reason why we want to do this is because earlier I was saying, ZT is very close to ZT minus 1, and we want our parameterization of mu to have this inductive bias of a residual form. So now, since mu only depends on ZT, we can parameterize it in the same way exactly. With the same scaling constant, since it depends on ZT, we can have a residual connection to ZT directly, skip connection. And for the residual part, we're gonna parameterize it to approximate the noise. Okay? So this part we're gonna have to input the ZT and also on time step. So like what happens at the end, since we want to match UT tail using U theta, we will match the right hand side. Okay? That means we can rewrite our loss term as a squared distance between the two epsilons. Okay? So front of you? Okay? So that means we go from predicting the mean to predicting the noise. Okay? With this simple parameterization of mean using noise predicting network. Okay? So this has the benefit of, our inductive bias tells us that, the mean should be very close to ZT. That's the first benefit. The second benefit, I guess, here is that to predict the mean, I guess, there's usually a lot of signals. And sometimes the mean can be large, sometimes it can be small. But by parameterizing the network to predict the noise, your target is usually, your target usually has a very similar behavior, no matter whether you are at a low noise limit or high noise limit. Your target is always from the standard Gaussian. In this case, it's just the fingerling condition are different. Okay? And everything in front of it kind of determines how much weight you want to add to your loss term. Right? However, in the original diffusion-based model, Jonathan et al., they realized that we can actually reweight the loss terms. So they found that if they weight everything by 1 instead of following this particular choice of weight, they can usually improve sample quality. There's various explanations for this. But my favorite here is that typically when you choose your beta and you follow lambda t, for t, so this is t. So for smaller time steps, usually you will have a higher rate. So for likelihood-based training, if you optimize the first with the correct weighting, you're gonna have a lower bound on the likelihood. You're gonna place more emphasis on smaller noise time steps. But for uniform weighting, you're gonna place more emphasis on also the higher level terms. Okay? And intuitively that also kind of makes sense. Because if you do this, you're gonna be better at predicting the contour of the noise in theta. Whereas if you place more emphasis on the lower level time steps, you're gonna focus on the high frequency features of your original theta.
One question: if we do this resetting, we are not actually optimizing the elbow anymore, but something else.
Yeah, good point. Yeah. So by doing this, you still have the value loss function, but it is not, a lower bound on the original marginal likelihood.
Putting it to one, is it not equivalent to the start you mentioned there is this beta t that we are multiplying. So if we at the start only put that we are not reducing. You mentioned that we are multiplying with the factor less than 1, so that we are constricting the our latent this z to a normal distribution with standard deviation 1. Would it not be equivalent to putting the beta t is equal to 1, beta is equal to 1 at that point, like in each latent space?
So beta, you can go back to the beginning. Beta is usually always 1, it's smaller than 1 in this like a one-way choice. So that is, at every single time step, you get slightly closer to standard normal, but not in one step.
So in the modeling part, we will still have this beta that we will multiply, but just the loss that we are minimizing, we are not.
Yeah, so in the modeling part, we will still have all of these constants here.
Okay.
Yeah, it's just in the loss, we just set everything to the 1.
Okay.
Yeah. So we set lambda t to the 1 to with the loss terms. That's why it's not low bound. Okay. Right. So if you do that, then your loss terms become very simple. So you just have you sample uniformly your time step because they are capital T steps, and then you sample Gaussian, standard Gaussian. That's the target, and this is parameterized ZT. You plug it in, and you take the expectation over your empirical data distribution, right? You want to maximize the likelihood of your empirical data distribution, and that's your loss. Okay, and a reconstruction that's ideally that's already perfect. Okay. All right. So just to recap, guys. So for training, we will exactly go through what I just said. We sample from a data distribution. We choose a random layer from 1 to capital T, or 2, depending on the index. We sample the target. We parameterize our ZT using this target, this random noise, and our original input data. So we corrupt the original data with this noise. We try to reconstruct the noise. Okay. So after it's trained, if you want to sample from prior, right? Standard Gaussian, and from capital T back to 1, I would plug this in, since the whole thing here is my new data, and add noise, scale by standard deviation. Okay, so we go through this procedure again to the noise, to go from something that's unstructured back to something that's structured. Okay, so we do this t times, and at the end we call z0 or z1, depending on your x, our sample. Okay.
Could you repeat again why we add again noise, like random noise on the sampling to ZT minus 1? Because we
Right.
subtract the predicted noise and then we add random Gaussian noise to the standard deviation.
So this is Gaussian for mean and standard deviation.
Oh yeah.
So this is the mean, this is standard deviation.
Okay.
Cool. All right, and results. Yeah. So first.
So for starting, we go through T up to 1 again, so we have to go through all of the different steps. But for training, we actually just sample from the uniform distribution. We actually have to make sure that we see all of the steps in the training, like all of the different T steps.
So this is exactly the benefit of the diffusion-based model. So it kind of decouples all of the loss terms. We can compute them independently. And we just want at the end, we want to approximate all of these things well. And we can stitch them up together. So you don't have to join and optimize the whole thing, because all of them can be independently trained. More questions?
Where do we get this sigma t security again? In the sampling part?
Yeah, because we assume our training model, the reverse process to be a Gaussian mean with data, which is this form, right? Because we parameterize it using the noise predictive network. So you have this residual form with and Gaussian with the variance square.
Yeah, but like it is written sigma t, so it is different for every layer, right?
In principle, it can be different for each layer.
So we decided beforehand only. It's not something that we are learning.
Yeah, it's an assumption that we didn't spend too much time on. Typically, you would choose it to match your forward process, so that you would have a close pointer typically, you would choose your sigma for your p to be the same as your beta for the forward process. So that for the KL divergence, you have the same distribution, then you have a nice close point.
One more question regarding this thing.
All right, so assuming you understand how it works for training and also how to sample form the model, if not, you can come to me after during the break, or or me or Victor. So this is the kind of samples you can get from diffusion-based models from 2020, which is like 4 years ago now, which is very impressive sample quality back in the days when the world of journey modeling was dominated by GANs, for instance. And this is like sort of the first kind of likelihood-based model or non-adversarially trained model that can achieve this kind of sample quality on I think it's Slab A and also CFAR 10. Yeah. So on the sample quality, they are very, very good. And in terms of likelihood measure, usually it's like the lower the better for negative likelihood on holdout set, and we can see that it is still at this point not on par with an autoregressive model like transformer, and later on there is some improvement, and I think diffusion-based model, I think they're currently the best in terms of both sample quality and also good likelihood measure, which is very impressive. And okay, so at the beginning of the talk, I was talking about some of the drawbacks of deep BAE and also flows. The primary one is that the space-time complexity of this model for training is growing linearly with the number of layers, growing with depth. So the more layers you have in the deep BAE, the more costly it becomes to train these models. Whereas for diffusion-based models, it kind of tackles this issue by saying that, okay, if we parameterize the inference network in a particular way, if we fix it and having a very simple Gaussian inference procedure, then we can decouple the loss terms into independent loss terms that can be optimized individually. And that will allow us to do simulation-free inference as well, so that we can sample directly ZT conditional on X without having to add noise iteratively to get ZT. And the second kind of benefit of a diffusion-based model is that we kind of fix this procedure, right? We say that, okay, we want to transform our data into the prior in this particular way. So there's no argument on, okay, is it better this way or better that way? We'll just fix it in this particular sample path from data to the prior, and we simply just focus on reverting the dynamics. There are also a lot of works that try to figure out if there's a better way to transform data into the prior, maybe in a more efficient way, like works that are inspired by optimal transport or something like that. You can also take a look at those. All right, and that's pretty much the main part of my presentation here. I just want to quickly mention that there's also different kinds of perspective, like score matching perspective with the diffusion-based model, which I won't talk about too much here, but you are encouraged to take a look at the literature. Just want to quickly mention the sort of benefits of having a score model. So when you're training this the noise network to predict noise, you can extract a score function out of this noise network. And remember, the score function is this gradient of the log probability. And if you have access to that, the benefit is that the score function, which is gradient of energy, which is the log probability, this quantity is composable. So we can use that to combine it with maybe a classifier you have pre-trained or trained separately to do classifier guidance, for instance, for sampling. So you can do conditional sampling easily with this kind of framework. You can also, I think there's also some work on energy-based model by composing energy so that you can sample a certain kind of concepts that is composable. You can also use this to sort of design your sampling procedure better. For instance, you can think about doing long-term dynamics more at a certain time steps to correct your sample, or you can accelerate the sampling procedure if you have this kind of viewpoint. And a paper that we did together with Victor and also some other colleagues was also extracting forces out of the noise predicting network, because force is essentially a concept that's very related to the score function in the molecular science. And here we see that if we train a diffusion-based model using molecular data, we can actually simulate a molecular simulation dynamics as shown on the GIF here. Yeah. And with that, this is the end of my presentation, and Victor will take over to talk about diffusion-based models using equivariant models.
Hello. Yeah, thank you for this very nice introduction to diffusion models. In the second and third section of this lecture, we will now explain a specific application of diffusion models for molecule generation. And then this is going to be short. We're just going to do a quick introduction to this. And then we're going to do a code and practice session in which we're going to code a diffusion model for molecule generation. The practice session, it's quite guided, so it's not like we're coding it from scratch. It's not something super difficult, but yeah, we will end up having a code that generates molecules using a diffusion model. The work on equivariant diffusion for molecule generation is based on this paper. This is a paper done during the PhD in collaboration with Emil, Clement, and Max Welling. And it was the first diffusion model for molecule generation. Basically, what it does is it maps from Gaussian noise to some molecule data that we train on two data sets, QM9 and GM DRAX. Why to generate molecules in 3D? So this is a topic that is growing a lot now. There's a lot of interest growing into the molecule generation, protein generation. It has applications, well, potential applications, especially maybe in the next years in drug discovery, catalyst design to accelerate chemical reactions, material discovery, which can also be key in things like designing new, more efficient batteries, solar panels, and also in docking problems, which is also related to drug discovery. So it's a very hot topic. There is now a lot of investment. Many companies like Microsoft or Google, or well, there is also new startups. It's something that it's really growing in the field. So yes, some background concepts in order to understand this diffusion generation, diffusion models for molecule generation. The first one will be just standard denoising diffusion. This is what Chin-Wei just introduced, so we're going to skip. And then another concept that it's also quite key in this molecule domain is the concept of invariance or equivariance. This is a very intuitive concept. Sometimes it can be introduced in more complex wording, but it's actually quite intuitive. So for example, we know that the energy of a molecule, it doesn't change based on its position or its orientation. So if we, for example, will use a neural network to predict what's the energy of this molecule, we will expect it to give the same value for any orientation or translation of the molecule. This will require, a way of doing this will be to introduce this constraint into our neural network that says for any orientation, just give me the same value. This is some prior we know, some inductive bias we know about our data, and we impose that into our neural network. The concept of equivariance is similar. Basically, we want that if we do a transformation at the input of the network, we expect equivalent transformation at the output. So this is, for example, very useful for predicting forces. If you rotate your molecule, you expect that the forces will rotate equivalently. Or if you just want to do a transformation on the molecule, you also usually want an equivalent transformation regardless of the orientation in many cases. So this is also a property that can be enforced in a neural network. Then we will say the neural network is equivariant to rotations. Another way to enforce these things is also, for example, with data augmentation. There are like these two ways of, the important thing is to be consistent with the symmetry of the data. There are ways that we can build a neural network such that it's equivariant. We could also take a network that is not equivariant and then do data augmentation such that we show it by data augmentation and the output rotates with the input just by rotating inputs and outputs in the same way. Both will be valid approaches as long as the end result works as expected. This concept of invariance or equivariance, it's actually used in many other applications, in many other networks. For example, in the first convolutional neural network, well, in general, convolutional neural networks are translation equivariant. Here we see the LeCun net, the neural network from Yann LeCun, like I think maybe now from 30 years ago. And what we want is, for example, we have a digit that is 0, regardless how is it located, like translated around maybe the patch that we're exploring. We want it to have the same label, so it still has to be 0. So we can achieve this by having equivariant layers, which means that the features at the output are translated if we do a translation in the input. This is a property of CNN that was very useful because it allows to share weight across the different positions on the input field, and the fact of sharing weights allows to train with much less data and still obtain very good or better performance. So there are many symmetries in the world that can be leveraged. In images, we were interested in translation equivariance. In molecular data, we are interested in translations to 3D, rotations to 3D, sometimes reflections too, depending on the application, and also to permutations. Permutations will be if we index differently the nodes in the array that we have in our computer. We will still expect a similar. We will still expect the same output. So this means, for example, if we have an atom represented as a vector of points with some coordinates associated, if we index these things, we are still representing the same atom. So we want the network to be permutation invariant or equivariant to those changes. The first two, translation and rotation, we call it E3 equivariance. And then the permutation, it's something that we can achieve thanks to, for example, graph neural networks or transformers. Those architectures are very useful, very commonly used in many applications. They share these let's say, advantage for some applications in which they are equivariant to permutations on the input data. In this work, in the equivariant diffusion models, we choose as a backbone neural network to use the equivariant graph neural networks. This is a neural network that we designed right before this diffusion models paper, and the goal of this neural network was to be very simple, very efficient, and still gives good performance. It's quick and easy to train. So right now, it's not the network that will give the best accuracy, but it's a network that's very easy to implement. It trains fast. It gives decent results. So yeah, let's say at that time was something that worked very well in the context of, for example, this workshop where we try to show a proof of concept. It's also very useful because it's very easy to follow the code, and it also trains very fast. So the work that we're presenting in the end is a diffusion model for molecular data. It's basically designed as a diffusion process that destroys the data. Then we have to find the denoising process to generate. These are the two processes that Chin-Wei explained. And in this case, we want to define these for continuous and for discrete data, because we're generating molecules, and molecules contain discrete data as the atom types, and they also contain continuous data as the coordinates. This diffusion model has to apply to the two of them. So we define the diffusion process on these two variables that we show here as x and h. X are the coordinates, and h are the atom types. The diffusion process is just as we see here, so similar that we saw in images before. At every timestamp, we add some noise following a conditional Gaussian distribution, and then we start from some data that ends up in noise. There is a trick when training these things. It's that we can jump to any time step, because the sum of Gaussian variables results in another Gaussian variable with higher variance. So if we would like to go directly from the data to a time step t, we can just use a conditional Gaussian with higher variance instead of having to do step by step. So the diffusion process, at the diffusion process, we can jump anywhere we want, not in the denoising. Then how do we do the generative part given this diffusion process? So we compute the reverse distributions. This is what Chin-Wei explained before, like how to compute this mean of the reverse distribution. So basically what we're doing is, well, we have to approximate the mean of the reverse distribution, and then we'll just follow this Markov chain from Gaussian to data samples. The result of this is this is just an image of the generative process of just Gaussian noise mapped to samples, like just random samples that we generate using this diffusion model. And then in the next slides, I'm going to explain how to train this. It's quite simple to train. Sometimes the concepts can be a bit more complex when we try to derivate all the equations, but in the end, what we end up with is very simple at the optimization stage. So to train this, we start with a molecule that we sample from our data set that has these x and h. X are coordinates, h are atom types. We add some noise to it. Let's see, okay, we add some noise to it. So to a given time step t and in random time step in this diffusion process. The noise we can see here, we have the noisy sample zt, which is the sum of the real sample plus some Gaussian noise, and these two things are weighted with the square root of this alpha and the square root of 1 minus alpha. So basically it's a weighted sum of the sample plus some Gaussian noise. That's what zt is. Then what we do is we take these, we input this noisy sample into a neural network. This neural network here is called phi. And then also the noisy step that we are. And then this neural network has to predict the noise that was introduced into this sample. This is the whole training process, like all the optimization. It's very simple. So basically it's the mean square error between the noise the ground truth noise that we added, and then the neural network has to predict that what was the noise that was added. So that's it. It just predicts the noise, and then it computes the mean square error with the ground truth noise. For this neural network, we are using the EGNN, this equivariant graph neural network, that what makes let's say the whole process equivariant, and what also in the end, I mean, this is proved in the paper, but this assigns, the fact of using an equivariant neural network here makes all molecules of different orientations, it assigns them the same probability. So there is no more probability for a given orientation than another. Any molecule will have the same probability to be sampled on any orientation. Then we use this neural network that we train using these very simple laws to parameterize the reverse function. So the reverse function, as mentioned before, it's a Gaussian distribution with a given mean that we are estimating. That mean is parameterized with this neural network. So that's it. Basically, we just need to learn this neural network using these laws, and then we take this neural network and then we put it into these equations of the reverse function that was a Gaussian distribution with a given mean, just by multiplying it with some scalars and summing some other values, we just parameterize the mean of this Gaussian. but the learnable part will be only this neural network here, that is just the mean square error. So this will be how this is trained, how this works, and then once we have this, we're ready to generate samples. The next part now is just the code and practice. For this, we have prepared a GitHub repository that links to a Colab. So this is, if you open this GitHub here, it's github.com/Vichy-Satorras ProbAI 24. Then there you will find the link to the Colab link. That's it. You open this. Once you have opened this, you will have to copy it to Drive so you can edit it. Just following these 3 steps here in the slides. And then everything is self-explained. I will also jump into it, so it's easier. So I will guide you through it a bit. But yeah, I will say the first step, just follow these 3 steps. Try to open the Colab, and then we can continue with the coding part. So once you have open this, basically, yeah, just follow the first steps of setup. If you get stuck on anything, just raise your hand, and then Chin-Wei and I will just come to your laptop and help if there is any issue with anything. Basically, you have the first is the setup. Then in the second part, there are 5 little exercises which are about coding the diffusion model. And then in the next sections, once you have this diffusion model coded, you will be able to already run it for 2 experiments. One is a toy data set of just 2 moons, and then after that you can move to the molecule generation. I will keep stopping and trying to maybe catch up or maybe give some hints if we get stuck somewhere. But yes, by now just try to follow the steps, which is installing first setting up the GPU, then just installing the environment, the cloning up the GitHub, installing the only dependency that is necessary. Yes, and then in the exercises, if you get stuck, just raise your hand and then we'll come to help. Okay, so I heard that maybe some people are getting an error here. It's actually not the error, but this is the check on the first exercise. So just to recapitulate, in the 0 section setup, it's basically running these 2 things. It's going to install the dependencies. And then when we move to section 1, code a diffusion model for a toy data set. If you read the instructions here, it directs you to the place where the coefficients are defined. And then the exercise is to define those coefficients. So we can find this we press the folder here. This is explaining the text, but still gonna do it here. So if we press the folder, we go to ProbAI source models, DDPM, the path that is shown here. That's the file that we have to edit. So we go to this file. So this is the file that we have to edit, and then we have the function get coefficients. This is the function that we have to modify, and then there is the type of the linear noise schedule. This is the one we have to do. It says here to do. Basically, we just need to do these 2 things here. Set the betas space between between this value and, just a second. Between this value and the beta min and beta max, and then set the alpha and alpha bars to following these equations. And if this is correctly done, when you run the test, it's going to see it's correct. Like now, for example, it's going to give an error because it's not correctly implemented. It's actually empty. The moment that this is implemented, if it's correct, then the test is not going to give an error. I'll leave some minutes and then I will give the answer after some minutes. So then no one gets stuck into this. I saw most of the people already solved the linear one, the first one. In case you didn't, I'm just copying here in the screen the solution for the linear one. I'm just gonna make it big so everyone can see it. Yeah, so in case if you're stuck in the linear one, this will be the solution. You feel free to take it, or maybe you wanna keep trying yourself, just don't look at it. So we are putting the solution for the second one, the one of the QMin and the QSTD. In case you want to take a look, this will be the solution, and if you want to keep working, just ignore it. So we are giving the solution to the loss. Well, there are many different ways to implement it. It's basically the mean square error loss and per sample in the batch. This is just one way of implementing it, but you can also use any built-in method in Torch that already uses like a method to compute the mean square error in PyTorch. But yeah, this will be the solution used in the exercise. The last one is in the screen, the one of the p-mean. This will be this part here. Yeah, so if you were stuck in this one, this is what needs to be done. I'll wait 4 more minutes, and then in the last minutes of the class, I will just go over a bit the script to show how it works, the molecule generation, and what is the expected behavior if everything was done correctly. Okay, so before finishing, I'm just gonna go over the notebook just to show what was the expected behavior. I saw some of you that managed to finish everything. So yes, if you manage to do these 5 PyTest implementations correctly, and then you had time to continue like the run with the correct diffusion model implementation. In the first section is just a toy dataset. The first section was just, well, first we plot this toy dataset of 2 moons, and then we train this diffusion model that you implemented when you implemented the cosine scheduler, the diffusion step and the reverse step. So we train that diffusion model on this data. The loss that you should expect is something like this. Once you train that, it's, as you can see, it's a bit noisy. It's because of the stochasticity of the Gaussian noise. The loss is really a estimation of the noise added into the sample that it's the input to the network. So that's very dependent on the noise. So then, yeah, you can see a bit of a stochasticity because the noise is stochastic. So it really has a big influence in the noise magnitude. After training for 100 epochs and then sampling, we get something like this. So you can see that the data set is recovered properly. It's a bit more blurry. There are some samples that are a bit farther away than in the original one, but this is just about matter of training for longer. And then in the next sections, we extend this same diffusion model for the molecule generation. The diffusion process is exactly the same. We just change the type of data that we input to it, which is the molecular data. But the diffusion, the noising and diffusion processes are the same, just adding Gaussian noise to this data and then denoising it. So it's actually the code is using the same implementation that you did and that has been used in the toy dataset. If you run this QM9 experiment, well, in the first section, this one mini QM9 dataset analysis, this is just analyzing the data, so you get familiar with it. This is a simplification of the QM9 dataset where just molecules up to 15 atoms have been taken. So it's a total of 19K training samples and 3.4K validation samples. Here you can see some stats of the data, like for example, the coordinates are like 15 times 3. This means like maximum of 15 nodes, times 3 is the coordinates. Then the one hot atom types is 5. This is because in QM9 we have 5 atom types. And then some other tensors that are used for the, let's say, the graph structure data in PyTorch geometric. If you plot the samples, this is still the data set. Nothing has been trained here. This is just analyzing data. You get some molecules from the QM9 dataset that look like this. Maybe in this, I mean, if we could rotate them, it will be easier maybe to see some structures. But yeah, these will be some samples that you can get. And Then there is still in this data analysis a valency test. It measures the atom stability and molecule stability. These are metrics used in the original paper. The atom stability, it measures how many atoms are stable in the molecule. And molecule stability considers a molecule as stable if all its atoms are stable. That's why it's lower, because as long as you have one unstable atom in the molecule, we say the whole molecule is unstable. Now what we do is we're going to train with this data the diffusion model, and then we're going to evaluate these metrics of atom stability and molecule stability. You can, again, just by using the code from before, there is one modification here that needed to be done. So some people, I saw some people that also managed to do this part. So this is basically just saying before we'll just input one x coordinate. Now we have to concatenate x, the coordinate space, and h, the atom types. This is the only change that needs to be done in the code in order to now work with the molecules. And yes, then if you run this code, it instantiates this data set. It instantiates the EGNN, the equivariant graph neural network. And then it starts the training. The training, maybe to start getting some decent results, it can take like up to 20 minutes, which is quite quick for a single GPU, but still it's not quick enough for the time we have in this session. So there is the option to load a checkpoint. This will be the option. So you can load a checkpoint that we trained before for, I think, maybe something like 30, 40 minutes, not too long. But it already produces some decent results. Then if you load this checkpoint and using the code of the diffusion process coded before, you can generate some samples. And then we analyze again this atom stability and molecular stability. We see that the atom stability is up to 0.8. This is 80% of atoms are stable. This is still not enough to get molecule stability. Because again, we say before that for a molecule to be stable, all the nodes need to be stable. So if we have 15 nodes, it's very likely that we find one unstable atom out of 15 if the probability is 0.8, but this will just be a matter of training for longer, like done in the paper. And then if we generate some of molecules using these, well, we just visualize some of these generated molecules that we use to obtain these metrics. We can see here that things start looking more like molecules. Maybe, for example, we can see there is a mistake here, but still, like the structure is like a ring from a molecule. So it's still not completely perfect, but we get the structure. We see that things start to look like molecules. And here we see something more like a chain. Yeah, so we start getting something that follows more the structure. So yes, this will be the whole session. Then this code is public, so you can just use this code. You can use the EGNN, you can use the diffusion model if you want for your own projects. One trick here is that actually all the solutions are present within the code. I didn't say it before the session, of course, but if you just go to when you import things here in the models, in this line, if you put ground truth here, like let's say the file is in models DDPM, that's the file you were working with. So now if you just add the ground truth here, then you just have access to the ground truth file. So you can use the code as it should, like as done in the solutions, by just adding this here. Yes, and that will be all. I think the session ends here. If there are any questions, we're still happy to answer them after the session. And yeah, I hope you enjoyed the workshop and that maybe this code is also useful for you in the future. Thank you.